Hello student, next we are learning as the second derivation, that is angular momentum. Angular momentum in terms of the moment of inertia. Now how to remember the formula for it? Again here the linear momentum P is equal to mass into linear velocity. Therefore linear momentum converted into the angular momentum. Angular momentum represented by L. Then mass is analogous to the moment of inertia I, and linear velocity is analogous to the angular velocity, that is represented by omega. This way we can remember the formula for the angular momentum in terms of moment of inertia. L is equal to I omega. Now come to the next point is that for the derivation of the angular momentum. Now again we consider a rigid body. This rigid body is rotating about an axis perpendicular to the plane of paper. This rigid body consists of this rigid body is rotating with a constant. Now here we consider a constant term is their angular velocity. Previously we consider the angular acceleration. Now we consider for this angular velocity to remember to obtain the formula for it. That's why in diagram already write here the omega. Means you will remember that this value is a constant in this derivation, and this is here to remember the alpha is a constant. Now omega is a angular velocity is constant. This rigid body is rotating with the constant angular velocity. Third point we consider this rigid body consists of the n number of particles having the masses is m1, m2, mn situated at a different position r1, r2, rn from the axis of rotation. When this rigid body is rotating, all this particle is performing the uniform circular motion, and when they are performing the uniform circular motion, in that case angular velocity is a constant and each particle is having the different linear velocity. That's why in diagram here it shows that the first particle having the mass is m1 and linear velocity is v1 situated at a distance r1 from the axis of rotation. This is a perpendicular distance from the axis of rotation. M2 second particle is situated at this position r2 and having the mass is m2. The linear velocity when it performing the uniform circular motion about the axis of rotation, then having the linear velocity is v2. For the n particle, linear velocity is vn. Mass of that particle is mn situated at a distance rn. In this way we draw the complete diagram of it. Now next is that as the object is rotate, all the particles perform the uniform circular motion with a different linear velocity. That's why we are writing the linear velocity formula for it. Linear velocity is equal to the angular velocity into the radius of it. That's why v1 is equal to r1 omega, v2 is equal to r2 omega, vn is equal to rn omega. The linear momentum. Now come to the next formula for it. Linear momentum of a first particle. Linear momentum of the first particle means the P is equal to mass into the velocity. If we consider the first particle, then in that case mass is a m1, velocity is a v1. Then substitute the v1 value of it, m1 r1 omega. Therefore p1 is equal to m1 r1 omega. p2 is equal to again m2 into v2, mass into velocity for the second particle. Substitute the v2 value of it, v2 is equal to r2 omega. After substituting of it, m2 r2 omega. pn is equal to mn rn vn, which is equal to mn rn omega. This is the formula for the linear momentum. Our aim is there to calculate the angular momentum. Then what is the formula for the angular momentum? Angular momentum is equal to the linear momentum multiplied by the perpendicular distance from the axis of rotation. It means it is a product of the linear momentum and the perpendicular distance from the axis of rotation. In magnitude, L is equal to P into R value. Therefore, L is equal to, for the first particle, L is equal to L1 is equal to P1 into R1. Then substitute the value of the P1, which is already calculated, M1 V1, which is equal to M1 R1 omega. Substitute this value, M1 R1 omega R1. R1 gives the R1 square. M1 R1 square omega. Second particle, L2 is equal to M2 R2 square omega. Nth particle is there. For nth particle, Ln is equal to Mn Rn square omega. In this way, we calculate the angular momentum for the each particles. Now, if you add this angular momentum, means resultant of the angular momentum of this rigid body, whole object of it, if we consider the value of it, angular momentum of a rigid body is the sum of the angular momentum of each particle. Each particle already we calculated. That value is added together, you will get as a total angular momentum. That is called as the rigid angular momentum of a rigid body. L is equal to L1 plus L2 plus Ln. Then substitute the value of the L1 is equal to M1 R1 square omega plus M2 R2 square omega plus Mn Rn square omega. Then again, if you see that in this term, omega is a constant taken as the outside of it, inside the bracket, M1 R1 square plus M2 R2 square plus Mn Rn square into omega. This is nothing but the summation of the Mi Ri square. I is equal to 1 to n, moment of inertia from the definition of it. Substitute here, L is equal to I omega. And this is our desired formula for the angular momentum of a rigid body. Now in this video, we learn the two important derivations of it. First derivation for the torque in terms of moment of inertia and the angular momentum in terms of the moment of inertia. For this, torque is equal to, 2 is equal to I alpha and L is equal to I omega. Thank you.